advanced algebra, and we're looking at exponential functions and using those to model population growth. Now we have the expression, the algebraic expression of an exponential growth, which is the equation y equals a times b to the x. Now every function that we use is a relationship between y and x being the independent variable, y being the dependent variable. The other variables in the expression then represent values from the data that we use to substitute in for a and b, and then using those values we're then able to calculate different y values for different x values and vice versa. So our job here then is to know what does A represent, so that when I go to the data I know what I'm looking for, and then I can calculate the value of A. And then I need to know what B represents, so when I go to the data I know what values I'm looking for and how to calculate it. So that's the way it is with all of our function models, is that the relationship is between y and x, and our job is to figure out the other variables and the value of those other variables that represent the data that we're looking on, so that when we substitute in particular x values we get a particular y value. So in the exponential model then, here's what the variables represent. The letter A represents the initial population. So when I go to the data, I'm looking for the initial population. In other words, when the study began, when the data begins, the first measurement that was made, what was the population? This may be the initial population in, say, a study on deer growth in a certain, section of the country. So how many deer were there when we began the study, and then we look at the data as it grew. The initial population, again, is very important to understand. The initial population will be when the x value is 0. This is huge. When the x value is 0, what's the initial population? Because the x, as you see in the diagram here, the x represents the years since the initial population, or since we began the study. So if I substitute in the value 0, that means no time has passed since we began the study. So what was the initial population? So that would be the beginning population before we start studying it, before any time has gone by, 0 time has gone by. How much population was there to begin with? So that's the relationship between the x value and the y value. So when we look at data, whether it be in a table, or whether it be a list of ordered pairs, or even if it's on a graph, if I find where x is 0 and I look at the y value that's produced, then that's going to be the initial population. So A represents the initial population. The x value, or the x variable, that's where I'm going to put the different amounts of time that have passed since we began the study, or since the initial population. Now, the letter B represents the growth factor, and I want you to pay very special attention to that phrase, growth factor, because we're going to be using another phrase later on that's very close to it, and they're two very different things. Okay, and we'll talk about those in just a moment. The growth factor is the value of 1 plus r. So in order to determine the value that goes in for B, I'm going to take the number 1 and add it to the variable r. And so r must be the question, what is r? Well, r is the rate of increase, or the percent of increase, written as a decimal. And again, it's very important. So how fast is this population increasing? Maybe increasing at 10% a year, 20% a year, 30% a year, 115% a year, or whatever. So you take that percent growth and you change it into a decimal, and you add 1 to it, and then that's the value that goes in for B. Okay? So the growth factor is determined by adding 1 to the rate of growth that's been written as a decimal. Now, as I said, there's a very big difference between growth rate and growth factor, and they are not the same. When we're looking at the equation y equals a times b to the x, the value of b is the growth factor. Okay? So whatever the growth factor is, that goes in for b. The growth rate does not go in for b, because the growth rate is not b. Very important notice. or thing to notice. The growth rate is the percent that something grows each year, as I said, or even decays. All right, so we may look at the data and see that the population of whatever we're looking at is growing at 10% a year. We do not put 10% into the equation. That's not B. Okay, we have to add 1 to that growth percent in order to figure out what the value of B is. So this is very important. And I know I've probably said that about 5 times already. I'll see how many times I've said it when I go to edit this. But anyways, the growth rate is not the growth factor. The letter B represents the growth factor, not the growth rate. In order to determine the growth factor, you need to add 1 to the growth rate. So the growth factor, or B, is equal to 1 plus the rate of growth, written as a decimal. So if the rate is 10%, you write that as decimal, you add 1 to it, and then that's the value that goes in for B. So let's look at a couple of examples very quickly here. If the growth rate is 17%, what would be the growth factor? So I take the 17% and I write it as a decimal. So I take the decimal point and I move it 2 to the left, and then I'm going to add 1 to it. So 1 plus 0.17, excuse me, is 1.17. So the value that would go into the equation for B is 1.17. That represents a 17% growth. Okay, so again, you can see the difference between a growth rate and a growth factor. At 200%, I move the decimal place over 2, so that makes that a 2. I add 1 to it, so the value for B that goes into the expression is the number 3. That represents the growth factor. That represents a percent growth of 200%. Okay, let's just take a quick look at one more, 0.055. Okay, so again, I move the decimal point over 2 to the left, so that's 0.00055, and I add 1 to it, so that gives me 1.00055. That would be the number that would go in for B into the expression in order to represent the growth factor. So again, growth percent, growth factor, two entirely different looking numbers. For an exponential decay model, the equation's the same and everything is exactly the same, except that the growth percent is going to be a negative number. So there's so you're going to feel like I'm dying here. An exponential decay model is exactly the same as an exponential growth. In fact, it is simply a fact where something is whose growth is declining rather than whose growth is increasing. So it's growth, it's just one's going getting bigger, one's getting smaller. And so the equations are the same. The values of the variables represent the exact same thing. We determine the value of B the exact same way. It's just that we're going to be adding a negative number. In other words, if the decay is 10%, that means the growth rate is a negative 10. So we're going to add 1 plus a negative 10. So in essence, we'll be subtracting the growth rate from 1 in order to get the growth factor. And again, growth rate and growth factor are not the same thing. So again, using the same number, if it's a 17% decay, then all I have to do is move the decimal point over here. It's a negative 0.17, and we're going to add 1 to it. Actually, we'll be adding, which amounts to subtracting 0.17 from that, and so 1 minus 0.17 gives us a 0.83. If we took 3%, we move it over 2 decimal places. That's 0.00. No, that's not 0.003. That's 0.03. I move it over 2 places. And again, because it's a decay, that's declining, we add 1 to it. 1 minus 0.03 would give us a growth factor of 0.97. Okay, so the only difference between a decay and a growth is that the percent is going to be either a negative percent if it's decaying, a positive if it's growing. Now there is one last thing I want to cover before we wrap this portion of the lesson up, and that is being able to recognize whether a equation represents a growth or decay simply by looking at the decay factor or looking at the B value. In other words, it's very easy, it should be very easy for us to quickly tell if something is an increasing function, meaning a growth, or a decreasing function, a decay, and that is totally determined by the B value, right? Because if we're growing, we're adding a decimal to 1, which means we're going to have a number larger than 1. If we're decaying, we're subtracting a growth percent from 1, so the number is going to be smaller than 1. So it's very easy to quickly identify whether we're looking at a growth or a decay simply by looking at the B value. Okay? And that would mean that if the value is between 0 and 1, it's a decay. If the value is greater than 1, it's a growth. So that's easy to tell. The second part of the problem or question would be, what would be the growth percent? Now remember, the growth percent is different than the growth factor. So this value that I see here is not the growth percent or decay percent. It's the growth factor. Now remember, if I added 1 to something in order to get B, in other words, if I added 1 plus the percent in order to get B, right? If I have B, how do I get the percent? Well, if I take this equation and I solve for percent, if I take the B value and I subtract 1, that's going to give me the percent. So to determine the percent increase or decrease, I'm simply going to take the B value and subtract 1. I'm going to undo what I did in order to get B. So for example, as I look at this first function here, I know that this first function represents a decay because this B value is smaller than 1. What is the decay percent then? I take the B value, 0.65, and I subtract 1. That's going to give me a negative 0.35. Now that's the decimal part. And now change it to a percent by moving it this 2 places to the right. So this is going to be a decay of 35%. So this equation represents a decay of 35%. Now you could write decay negative 35, or if you just wrote decay 35%, that means the same thing. Decay and minus 35 is a little bit redundant. It kind of says the same thing twice. A couple more examples and we'll wrap this up. This value here is larger than 1, so I know that this is a growth. In order to figure out the growth percent, I take the B value, 1.63, and I subtract 1. 1.63 minus 1 is 0.63. Now change it to a decimal, or change it to its percent by moving it over 2 places. So this would be a 63% growth represented by this equation here. Alright, the next one here, the B value again is larger than 1, so this is a growth. B value 1.3 minus 1, that gives me a value of 0.3, move it over 2 places, so this represents a 30% growth equation or exponential function. The last one real quick here, this is less than 1, so this is a decay. The B value is 0.25. 0.25 minus 1 gives me 0.75, negative 0.75. Move it over 2 places, so this would be a 75, ooh, I didn't write that, a 75% decay represented by this expression. Okay, so main things here, remember the difference between growth percent and growth decay. In order to figure out the B value, you add 1, and the A value represents the initial population, or the initial population, remember, represents the initial value when the X value is 0. So substituting in 0 to the expression, that produces the A value.